Okay, so for this video, we will discuss about some solved problems in earthquake engineering. Okay, so number one, a mass hangs on two ideal springs as shown. What is the total composite spring constant for the system? So in this kind of system, the total stiffness of the system is simply the summation of the stiffness of each spring. So if you have two springs here, so simply the K total is K1 plus K2. If you have three, K1 plus K2 plus K3. Okay, so this is the answer. So for number two, we have a problem like this. So each of the following pendulum with equal mass are hanging on an ideal spring. So this has equal mass, these two pendulums. The period of vibration for the pendulums are 1.73 seconds for this and 3 seconds for this. So assume the pendulums are on frictionless pivots. What is the stiffness of the second pendulum spring? Okay, oops. Take note the the s- the period of this system is 2 pi square root of m over k. So similar with structures, the period of a building or structure is this, 2 pi square root of mass over its stiffness. If you will observe on the problem, they have different period, okay, but equal mass. So what could be the difference also? If they have the same mass and it you have different period, therefore their stiffness is also different. Okay. So they have equal mass. So we can lay down the formula like this and then plug in the corresponding period. So for T1, 1.73 equals 2 pi square root of mass 1 over stiffness 1. For the second system, 3 seconds is equal to 2 pi square root of mass 2 over K2. But mass 1 is equal to mass 2. So as you look at the equation, we can just raise both equations by 2. Okay, so if you raise that, we can eliminate the square root sign on these two equations. Okay, so 1.73 square is equal to square of this is 4 pi square mass 1 over k1. While on the second equation, 3 square is 9 equals 4 pi square m2 over k2. Okay, so since mass 1 and mass 2 is the same, therefore we can this 4 pi square and m will cancel out, right? So we can just relate these two equations by 1.73 square k1 is equal to 9 K2. K2 will be transposed here. Okay. K1 will be transposed here. Okay. So 1.73 square K1 is equal to 9K2. Or simply, if you divide both sides by 9, you will get this, wherein 0.333 K1 is equal to K2. In short, the stiffness of the stiffness of this one is 1/3 of the stiffness of K1. Okay, so this system 1 is much stiffer. Makes sense because system 1 has a shorter period, so therefore it has greater stiffness, whereas system 2 is 3 seconds, almost double of the period of the system 1. Therefore, it's more flexible. Okay? Okay. So next problem. Okay. So each of the following columns support a block of identical mass, M. The columns are fixed at the bottom and free at the top. The height of the second column is twice the height of the first column. Okay, here. The modulus of elasticity and moment of inertia for both columns are the same. Okay, so let's say they are both steel or they are both concrete, and their cross section is the same because they have both the same inertia. The systems have natural periods of vibration T1 and T2 respectively. Neglecting the weight of the columns, what is the natural period of vibration for the second system? Okay, so we have a cantilever system. Okay, take note the stiffness of that system is 3EI over H cube. Okay, how do we get that? Example, remember a cantilever beam. If you idealize a cantilever beam, this one, and then you have a concentrated load at the rightmost side. So what is the maximum deflection of that? So this is P, this is L. Your delta max is actually PL cube over 3EI over H cube. Okay. From the formula of stiffness method, P is equal to KU. Okay. What is our U? This delta max. So we have P, we have U. Therefore, if we rearrange that, you will get P is equal to 3EI. Okay. 3EI H cube. I'm sorry. 3EI H cube delta max. Uh, sorry. This should not be H cube. L cube. 3EI L cube. 3EI over L cube. Sorry. There. Okay. So P is equal to 3EI delta max over L cube. Okay. So this is your P. This is your U. So therefore, this is your K. Okay. 3EI over L cube, which is similar to this. So kumbaga tinayo lang natin itong cantilever beam such that naging structure siya. Okay, because we're talking about lateral displacement. So we're talking about lateral stiffness. Okay, kumbaga pag ito nag-displace from the earthquake, so ito yung lateral displacement na tinatawag natin. We have lateral force there. Okay, so lateral stiffness yun. Okay, so 3EI over H cube. So yun. So setup natin, K1 is equal to 3EI over H1 cube. K2 is 3EI over H2 cube. But take note, H2 is twice the H1. Okay? So rewrite natin siya dito. K, since ano naman, no? Same yung elasticity, same yung inertia, because same yung cross section. So maka-cancel out lang yan. I-relate ngayon natin yung dalawang K1 and K2. So H1 cube will be transposed here. H2 cube will be transposed here. So K1 H1 cube is equal to K2 H2 cube. Okay. K1 H1 cube is equal to K2. What is the relationship of H1 and H2? Twice, diba? So if you cube 2, that is 8. So this should be, sorry, this should be 8 H1 cube. 8 H1 cube. Okay. So cancel out the H1, you will get K1 is equal to 8K2. So therefore, since double yung height ng H2, therefore yung stiffness nung system 1 is 8 times the stiffness of K2. Okay. Okay, so we have now the relationship of K1 and K2. Okay. So let's lay down yung formula ng period, 2 pi square root of m over K. Okay. Then it's like what we did earlier, square natin both equation para mawala yung square root sign ng m and k. So t1 square is equal to 4 pi square m over k1. T2 square is equal to 4 pi square m over k2. Since the same yung mass, okay, so k1 will be transposed here, k2 will be transposed here. So t1 square k1 is equal to t2 square k2. Then let's substitute yung relationship ng k1 and k2. So t1 square is 8k2 because yun yung k1. Then is equal to t2 square k2. Okay? So t1 square is equal to 1/8 of t2 square. Of course, let's square root both sides, okay? And then find the relationship of T1 and T2. So we have T1 is equal to 0.3536 T2. Or kung babalik ta rin yan, you have 2.83 T1 is equal to T2. Or roughly, yung period ng T2, yung mas mataas na structure, is 3 times ng period ng mas maliit na structure. Okay? So, ganun yung epekto, no? Mas twice yung height niya, yung epekto niya sa period is 3 times. Okay? Of the 3 times of the period of the first system. Okay. So, I think this is the next problem, the third problem. So, we have say a one-story building wherein there's a force acting at the top of this one-story building na may tatlong poste. Okay, the supporting columns are of equal height, okay, as you see, and fixed at the base. Assuming the modulus of elasticity is the same, okay, say concrete or steel. Assuming the top plate is rigid and I1 is equal to 1/3 daw ng I2 and also 1/6 of I3. Okay. Oops. Now, this is no longer a cantilever idealization. So, fix na yan. Fix din to because we assume the top plate is rigid. So, you can just assume, let's say, meron kang roof deck, tapos meron kang one-story structure, tapos concrete yung slab mo. So, parang ganyan yung idealization. Therefore, it's fix, no? Hindi siya cantilever. Okay. Fix yung support ng poste. No? Okay. So that the stiffness of that is 12 EI over H cube for fix. Unlike sa cantilever, 3 EI over H cube. Okay, kasi yung sa cantilever, we idealize the overall, where's that? Structure. Okay. Dito hindi. Uh, Kinuha talaga natin yung framing, no, elevation. Okay. 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 So if I were able to derive yung 3 EI over H cube, how will I derive this 12 EI over H cube? So madali lang 'yon, no? If you remember yung moment distribution method, maglagay ka ng lagay ka ng delta here, no? Ayan. Tapos dahil fixed to, no? So, indeterminate na to, no? You can derive this 12 VI over h cube by area moment or slope deflection method. So, you will observe that delta is equal to actually 2 uh, that P times uh, h cube over 12 EI. Okay, unlike sa as compared to dun sa cantilever, diba, it's L cube over 3 EI. Okay. Now, so how do we determine the shear on each column? So simply based lang naman yan sa proportioning ng stiffness. Okay? So yung total base shear F multiplied mo sa stiffness. So say you wanted to get the shear dun sa first column. So total base shear times stiffness of the first column all over the summation of all the stiffness. Okay? So ganun din, no? So V2 total base shear times stiffness ng second column all over summation of the stiffness. Then last, shear sa third column is equal to force or the total base shear times uh, stiffness of the third column over summation of K. Okay, but first, let's find out the summation of stiffness. Okay, for K1, it's 12 EI1 over H cube. For K2, 12 EI2 over H cube. Okay, ginamit na natin itong formula na to. For K3, it's 12 EI3 over H cube. But, no, so, but we have the relationship of this, right? So, gamitin natin itong relationship na to. Wherein I1 is equal to 1/3 I2 is equal to 1/6 I3. Okay? So, summation of K or stiffness is equal to 12E. Extract natin, no? E kasi E is ano naman, similar in all columns. Over H cube, isa lang naman yung height. No? Then, I1 plus, what's I2? Siyempre, yung 3 here, transpose mo, that will be 3I1. What is I3? So, transpose mo yung 6, that will be 6I1. Okay? So, 12E over H cube times 1 plus 3 plus 6 is 10. So, 10I1. So, your total stiffness is 12E over H cube times 10I1. Okay. Then, since ang tinatanong is uh, what is the shear at the first column? So, substitute lang natin, no? So, V1 is equal to F times K1. What is K1? 12EI1 over H cube. Then, what is the total stiffness? Ito yon, 12E over 10I1 over H cube. As you notice, marami tayong maka-cancel out. Yung 12E, yung I1, saka yung H cube. So, ang matitira na lang is 1 over 10F. Okay? So, therefore, yung shear sa first column is 10% lang ng total base shear. Okay? Bakit kaya? 10% lang, no? Kasi as you notice, no, 1/3 lang siya ng I2, yung stiffness nitong first column. Tapos 1/6 lang siya ng stiffness ng I3. So, mas stiffer itong I2 at saka yung I3. Actually, mas pinaka-stiff si I3. Na sumunod si I2, last si I1. Kaya siya yung pinakamalit na shear sa base shear. Okay. Okay, for the last problem, okay, in the response spectra shown, what is the base shear? So I've told you, no, yung response spectra is yung plot ng acceleration versus period. No? So what is the base shear daw? Assuming yung weight of the structure is 712 kilonewton. And then yung period ng structure is 0.3 seconds. Ayan. So, dali lang, no? Base shear is actually force equals MA, di ba? Newton's formula. Now, given yung period na 0.3 seconds, Okay, ito yung, as you notice, nasa gitna yung point 3. Then, plot natin yon using the response spectra curve. Uh, as shown here, no, yung acceleration niya is 0.7. So, yung acceleration is 0.7 g. Okay. So, F is actually the base shear. So, substitute lang, no? F is equal to mass is this, 712 kilonewton over 9.81. Actually, because 712 kilonewton is actually W, di ba? Then the acceleration is 0.7 g. So 0.7 times 9.81. So maka-cancel out lang yung 9.81. Or simply, your base shear is zero point 0.7 times 712, which is 498.3 kilonewton, or roughly 500 kilonewton.